Thank you everyone also for joining. There are some more participants coming in. So first, it's a true honor for us to introduce our keynote speaker today, Professor Susan Athey, one of the pioneers in causal inference. Professor Athey is the Economics of Technology professor at the Stanford Graduate School of Business. In an interview some years ago, Susan, you said, "My prediction is that economists are going to become more like engineers." And that is, of course, not only true, but also reflects a bit your own curriculum, if I may say that very short, because your journey as a technologist began already as a child when you programmed a sound simulator on a Radio Shack TRS-80 computer. And you even published that, I've seen, in the computer or color computer magazine together with your father. So that is quite impressive. And after earning your bachelor's degree in computer science from Duke and a PhD from Stanford, you joined the economics departments of MIT, Stanford, and Harvard, where you then also became Harvard's youngest tenured professor. Yes, and if that is not enough, you have another extensive list of honors, including the election to the National Academy of Sciences, being the first woman to receive the John Bates Clark Medal. You served as a chief economist for the US Department of Justice Antitrust Division and as a president of the American Economic Association. And most important in our context, as we are about industry meeting academia, you were also one of the first tech economists and have also written a paper about it by serving as a chief economist at Microsoft for about 6 years. And more recently, in 2019, you founded the Golub Capital Social Capital Lab at Stanford, which applies social science to improve the effectiveness of social sector organizations in health and education, for instance. I highly recommend everyone here to check out the website and projects. It's really interesting. Last but not least, beyond your research, you are a dedicated mentor. You champion diversity and support young economists, particularly women and other underrepresented groups we have seen. And yeah, we hope it's fitting that this conference has this year, for the first time, achieved about 30% participation rate from female attendees, which we are proud of. It was also hard to push the needle, if we are honest, but of course, there's also some more room to improve. And in that regard, we are also very thankful to have you here today as like a leading female representative, so to say, in the field. Yes. And I would say thank you, Susan, and the stage is yours.
Great. Thank you so much. And thank you so much for having me. And wow, what an introduction. I feel like I have a lot to live up to now. So I wanted to talk today about some research I've been doing that's a little different than what some of you might know me for. I just went recently to a conference and some people came and said, "You're Susan Athey. You're the GRF Susan Athey." And I was like, "That's great," and they're like, "Oh, you're an economist. I didn't know that." Okay. So people know you for different things, and I'm so excited that the work that we did has been impactful in tech firms. This paper or series of papers I'm going to talk about today is kind of a new direction for me in trying to bring in neural networks and transformer models into some kinds of causal inference problems that we can study. So let me get started and share my screen, and I'll show you this great team of people I've been working with. So the team includes Kian Bafa, and the work I'm going to talk about most today was led by him when he was a PhD student, and he's now a postdoc at Harvard, and he has a degree in computer science. Some of my students now, Tianyu and Herman Brumberg, are engineering students here at Stanford. Ayush Kanodia was a CS PhD student. Emil Palico is starting in marketing next year at Northeastern, and he was my economics postdoc here at Stanford as an econ background. And David Bly is PhD and is a professor of stats and CS at Columbia. So really an interdisciplinary team of people trying to think about what we can learn about doing causal inference using some of these modern methods. And I would say that I have a couple of motivations. We're going to study careers and labor markets. And one reason I'm interested in that problem is that I go to a lot of conferences and so on where people ask me questions like, what are we going to do about AI and jobs? And what are we going to do about technology and jobs? And so one thing I've been trying to think about is how to use technology to help people with jobs. But there's another reason as well to study this particular class of problems. I want to, these LLMs and transformer models are so important. People are using them everywhere. And I really want to understand them. But to understand them, I need to dig into them. And it's really hard to dig into like language. And we see that people are really struggling to make sense of what does interpretability mean, what does bias mean in the language models. And so what I'm trying to do here is myself to dig in and understand these class of models in a laboratory that I can play with, that I can work with on GPUs at Stanford, and where the problems are sort of more concrete and more narrow. And I want to build out my intuition from that. And so that's another way to think about what I'm doing. Like just as a scientist, you get overwhelmed if you're just like dropped in this morass of problems and you can't figure out how to analyze your data or analyze a model. And so it can be really helpful in my experience to really focus on solving one problem. And along the way, you learn a lot. And that's actually one reason I like to collaborate with firms and social impact firms, and in the past, a lot of for-profit firms, is that in the end, when you're pushed to solve a problem, you think differently and you learn in a way that you can't when you're just staring at your chalkboard. So to try just to kind of really high level think about, you know, how AI can be used in causal inference and causal modeling, there's a lot of different approaches that people have already been using for the past, 15 years. And I want to just pop back and categorize them a little bit so that we can put what I do today in context. One of the first things that people did with modern machine learning and AI in causal inference and social sciences was to try to use take things like text and turn them into lower dimensional vectors and stick them into regressions. So X's might be predictive features. Like I might want to predict what words lead to star ratings in reviews so that I can understand whether a review is positive or negative. So people did that in marketing. I might want to use the speech of legislators to predict whether the legislator is Republican or Democrat. And that way I can understand, what words people say are correlated with being Republican or Democrat. So just in terms of like predictive features, you take text, you turn them into X's, predictive features, and you stick them in a predictive model. They might also be used to control for things, and that's what I'm going to be using them for today, as trying to adjust for confounders, basically. So I'll be talking more about that, so I'll come back to that one. You also, though, could use features or embeddings or representations extracted from text or images as a treatment. And so, for example, you could see whether reviews lead to more purchases or more visits to restaurants. And, I have some work doing that. But that was very common. So you're taking something like text and you're turning it into a lower dimensional object, and you're seeing what's the effect of that object on something else. In the bottom right of this slide, I have a picture, two images. This is from a paper I wrote where we were trying to understand the causal effect of different ways that people presented themselves in their profiles. And so in that study, we were studying the Kiva lending platform, which is where people probably from high income countries make loans to people from low income countries. And the borrowers have profiles, which is of course very similar to like profiles for Uber or Airbnb and so on. And there's already been a lot of research showing those profiles can affect outcomes for people. But a lot of the previous studies tried to, when they used real observational data, they tried to adjust for everything that else was similar and isolate, say, the effect of race. But that's difficult because, people with lighter skin may also, have other things in their background. There might be other aspects of an image other than their race that viewers are picking up on. So one of the things here we did was we actually created alternative versions of the same picture that only changed in one dimension, and then put those in front of lenders. And that helped us isolate the causal effect of the smiling. We actually used that, and we also used causal inference techniques. And we showed that actually in the case we studied, that we got the right answer from trying to adjust from confounders in images. But many other studies that have tried to compare observational study techniques that try to adjust for confounders to experimental techniques have found that those didn't give you the right answer. So it's not something you can take for granted. So this study tried to just vary one dimension of an image, which was a smile. So that would be a feature that you can determine from AI that can be used as a treatment. And of course, you can also use machine learning and AI to take things like text and images and use them as an outcome. For example, in the case I was just describing, one of the counterfactual policies we evaluate is, what if you told everybody to smile more? So we haven't done that, but if we did, we could send out a nudge to everybody and tell them to smile. And then we could look at the pictures and see whether, in fact, we had succeeded in getting people to smile. So it could be an outcome. So to summarize, it's what we have been doing in the past 15 years with machine learning and AI techniques is, in the context of causal inference estimation, is we've been like turning these complex things into either confounders, observed confounders, or control variables, treatments, or outcomes. And of course, you can also look for treatment effect heterogeneity as well with respect to features. So in that context, what's changed with the latest neural nets is just like we got better predictions, and maybe we can do more. Maybe this whole enterprise will just get better, because I've tried many times to work with text with small data sets, and it didn't really work very well. Like, we just couldn't understand the text well enough to create high quality features. And so there are many projects on the cutting room floor from all of that. But now these things work better, and they work better with smaller data sets, and so we can do more with them. Another thing that you can potentially do is model panel data or sequences of outcomes. And that's going to be one of the focuses for me today, although I'll still fit it back into this framework of controls in my setting. But in general, we can also think about these techniques as being particularly good, the recent ones at doing dynamics. And so that might open up problems where in the past we thought we just didn't have enough data to make progress. And so I think that's an interesting open area. Of course, there's lots of other things we do with AI too. I'm not going to have time to talk about all of those now. Just I have a bunch of them on the slides. Differential privacy, semi-synthetic simulations with realistic data sets can be created with AI. I've done some work in the pandemic on federated learning, where you get data, you want to do causal inference with data from lots of different hospitals without pooling their data. Lots of things we can do. We also can do fancier experimental design. We can do, reinforcement learning, contextual bandits, online learning, all of that stuff. So those are things I worked on separately. But today I'm going to focus in on these language models. So now I said I had this specific area we were going to work on. I haven't talked that much about that yet. I'm going to be working on worker careers and data about worker careers. And so many of you aren't labor economists, so let me do a little bit of motivation. So in labor economics, there's a couple of really popular questions that have tens of thousands of citations, hundreds of thousands of citations, like just problems that many, 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 many people study in different data sets in different countries in different time periods and so on. One of the big things are called wage decompositions, and I'm going to focus on the gender wage gap, which is very popular, but you can do racial wage gaps, education wage gaps, urban rural wage gaps, all sorts of different kinds of decompositions. And so decompositions are actually not causal questions. They're explicitly not causal. They're just asking how much of the difference between two groups can be explained by covariates, by if you have a worker at a point in time, how much can be explained by what came before. But it turns out that solving that problem is isomorphic to solving a causal problem, and all of the estimation tools are equivalent. And so but that could get a little confusing. So before everybody goes to sleep, I just want to highlight that point. I'm going to be talking about decompositions, which are not causal, but I'm going to use causal tools. I'm going to slip a little bit into talking, going back and forth between them. But just what the reason I go back and forth between them is the only thing that's different between a decomposition and a causal question with unconfoundedness is the statement of the question. The estimand and the methods are the same. So that's why this is a tight connection. Causal questions might be, what's the effect of a job training program on productivity? Say conditional on education and history. And so in those settings, there's been a lot of kind of unconfoundedness type techniques. The labor economics literature has done a lot of linear regressions, like thousands and thousands and thousands and thousands of linear regressions to adjust for things. But there's a part of that literature that also uses semi-parametric techniques and is more methodological in focus. But in general, you call these we think of like wage regressions, where you're trying to look at the causal effect of something on wage, and you use a regression to adjust for other things that might make workers similar. So what we have done, and especially in the US, we do not have good data. Especially, we do not have good data tracking people over time. We have a couple of big survey data sets that are available broadly, and those have tens of thousands of people in them. Unlike, Scandinavia or some European countries or other countries around the world, we do not have data available broadly to researchers that follow workers over time. More people are getting access to some of these confidential data sets, but even like IRS data, people self-report their occupation, and their firm, but you really don't have the kind of granular information that we would have in other countries. But most people don't have access to that data. So what people have done is they run regressions, and when they try to adjust for things that might be different about worker histories, they use handcrafted summary statistics in simple regression models, and that's been the practice. So the question is, can machine learning and AI provide better methods? And some of the challenges, I think, in doing that have been data size, data availability, and also something that's been a theme in the causal inference literature, potential, if you bring in machine learning, you may end up with regularization-induced biases and create omitted variable problems that you don't understand. So I think people have been a little bit still cautious about bringing in modern techniques. Just to make that a little more precise, just remind, I'm not sure everybody here is familiar, but just to get the notation down, the standard unconfoundedness setup is a setup where there's two potential outcomes: your outcome if you had been treated, your outcome if you were control. And unconfoundedness assumption says that conditional on your characteristics, those potential outcomes are independent of the treatment. And there's theorems that say that under unconfoundedness and an additional assumption called overlap, you can estimate average treatment effects if you have a big enough data set. And the overlap assumption just says that for any particular vector of x's, there's some probability that you're treated and some probability that you're control. So you have some ability to learn about those people. There's some observations of those people in both the treated and control group. And so the methods that are used rely on predictive models in one way or another. There's many different ways you can estimate average treatment effects, all of which have different properties. Many different ways are efficient to a first approximation. But the two components of the predictive model, one would be a propensity score, an estimated probability that you're treated, and the other would be an outcome model that is a conditional expectation. Oops, there should be a W next to that mu hat. A conditional expectation of your outcome given your treatment status and your X. And the state of the art are doubly robust methods that use machine learning to estimate the E hat and the mu hat. And what's very popular now are things like augmented inverse propensity weighting or double machine learning, double robust estimation, all kind of roughly synonyms from a high level. These are techniques that try to reweight the data to make the treated and control group similar, and also try to use outcome models to adjust for differences. And the theorems basically say you need a good quality outcome model and a good quality model of the probability of being treated as a function of your covariates. And if both of those are good enough in terms of the product converging at the root n rate, you can get an efficient estimator of the average treatment effect. Now that's a nice theorem, and it says prediction matters, like the ability to estimate these predictive models matter. A lot of the literature in the applied literature, applied econometrics, applied statistics literature has focused on details. And one theme is that how you do the estimation matters. And we have to pay attention to what we call regularization-induced emitted variable bias. And there the idea is that if we're trying to do these prediction problems, especially if we just try to use lasso regression models, outcome models without weighting, we can run into a lot of problems because if we there might be x's that are very important that are very correlated with both treatment assignment and outcomes, but they're not the most important things for predicting outcomes. And the worry is that in fitting mu hat of n, when fitting this conditional mean function, I might leave out x's that are more weakly correlated with outcomes, but that are strongly correlated with treatment assignment. And that would lead to bias. And so that's something that's been pointed out over the last 15 years, that you have to be very careful when you do this estimation. And so that's been part of the theme of the causal inference literature, is that, yes, you can take a causal inference problem and turn it into a prediction problem. If I can get those mu hats and e hats as prediction problems, I can do well. But there's still a cautionary note, be careful, because causal inference problems are different than prediction problems in that we care we care in small samples where we're maybe racing against with complexity against the sample size. We may make mistakes of leaving out x's that are really important, and those would be, once they're omitted, they may be observable, so hypothetically we can adjust for them. But if in doing our machine learning we drop them, like in a lasso, if we regularize them out, but if we don't pay enough attention to those x's and fitting our models, they will be as if they were unobserved confounders and create emitted variable bias. So these are some of the lessons that we have from the existing literature. I'm just summarizing, 30 years of research, because people worked on these same problems with kernels before they had machine learning. Okay, so that's the background. Now let me talk about foundation models, another kind of bit of background. Foundation models, that term was coined by my colleague. Actually, I was one of the co-founders of the Stanford Institute for Human-Centered Artificial Intelligence, and one of our big funding initiatives was we funded my colleague Percy Lang with the Center for Foundation Models, coining the term foundation model, which was very prescient. And a foundation model was the idea that you're going to use a lot of data to create a model that has a general understanding of the world, and then later it can be applied to downstream tasks. And some big ideas on that. One is that it's self-supervised. So for text, we can take one paragraph and treat it as a bunch of next object prediction problems without any structure, without cleaning or normalizing or doing anything else to the data. The second big idea is embedding functions. So we're going to transform high dimensional data into lower dimensional vectors. Of course, now that might be 1,000 dimensional vector or 4,000 dimensional or 8,000 dimensional vector. So they still can be very big vectors. In the case of OpenAI, a lot of the Llama models have 4,000 dimensions, but it's still the space of a 4,000 dimensional vector is much bigger, smaller than an indicator function for every possible sequence of words in the English language, which clearly very quickly gets larger than atoms in the universe. So the third idea, and this is not always used, but this is what we're going to be exploring in our paper, is fine tuning. And that is, once you have a foundation model, then we can continue the training on more specialized data and get it to do well at our specific tasks. And so this concept is, although you don't hear about it as much in the newspaper, it's very common in practice. What I've seen a lot of companies telling me about how they are able to achieve performance similar to OpenAI if they take a llama model and fine tune it. And that's going to be one of the things that, we find in some of my research as well. This is, but from a scientific perspective and from a researcher perspective, this is amazing, because you might think, oh, well, I can't do research on foundation models because I don't have a couple $100 million or a couple $1 billion and a bunch of GPUs, so I can't participate in that. But actually, the fine tuning part of it, everybody can participate. It's cheap, it's easy, and there's a lot of tools available to do it. And so I've been doing tons of fine tuning at Stanford on our own GPUs, and it's actually like much easier than a lot of other things I've done in my life in terms of like how much coding there is and how good the tools are to do it. But the second thing that's important about fine tuning that I'm going to highlight is that fine tuning is just minimizing an objective, and we can change the objective. That's the brilliant part. We don't have to use the same objective that Meta did when they trained Llama. We can use a different one, and so therefore I can optimize that for whatever I want, including causal inference objectives, and that's going to be part of the agenda. So really detailed questions here. First, in general, can foundation models improve empirical economics or applied causal inference? If so, should the researcher custom create them, or should they use off-the-shelf models? Do they have value? And what's the interaction between model size and data size and diversity? And so my journey was, we started building custom transformer models before OpenAI released ChatGPT. And I was excited about those, and I'm going to show you results from those. We have been finding, though, recently that we can do just as well or better fine-tuning the language models and the public open source language models, even for problems that didn't seem like language problems. And that's a kind of a cool insight. And we are also finding that you can do better by adding data to a smaller model size than using a bigger model size. And that can be really important for researchers in terms of tractability, because smaller model sizes are easier to estimate and easier to work with on small machines. So getting more data may be more important than using a really big model. And so then really for the purpose of this audience, I want to talk about how to tailor fine-tuning for causal objectives based on the theory that we've already developed, and also think about what new questions and opportunities arise. I would argue that it's been very common in economic causal inference to throw away most of the variables in a data set and focus on a small number and handcraft them into summary statistics. But once you have very flexible models, you can much more easily incorporate much more different types of data. There's much less data engineering, much less feature engineering, much faster to change your schema. You can just throw things at some of these models and without doing much work, and that's really exciting. Okay, so I'm going to start with the first paper, which was published in Transactions for Machine Learning Research in 2023. This is our first hack at this custom foundation model. So here we're going to put in that paper we think about how do we build a model predicting wages. There's lots and lots of histories of worker careers. So these are examples of worker histories. So I could think of all possible histories and now say there's 300 and some jobs. So there's many, many, many possible sequences of 300 jobs. So there could be a very large space, and I could use indicator variables for whether or not you have a particular sequence. Obviously, that would be more than the number of people in the world. So I can't actually estimate all of those parameters for each possible history. So I'm going to have to do some kind of smoothing. Coming up with a mapping from histories to a lower dimensional representation is going to be one way to do that. But we don't have a lot of data, like in the data sets that we have, the public survey data sets with wages, they're very small. So what we did instead is we built a custom foundation model using scraped resumes off the web, about 23 million resumes. And the thesis is that the representations of sequences of histories that work well for predicting the next job in the sequence might also be related to what's important for predicting wages. Could be wrong, could have nothing to do with it. It could be that what's important for predicting your next job has nothing to do with predicting your wage, but seems likely they have something to do with each other, and we're going to show that in fact they do. And our foundation model is helpful. So the publicly scraped data sets of resumes do not have wages. These are just like profiles that people post on the web. They don't have wages. If they did, they wouldn't be verified. So we don't have wages. But they do have sequences of jobs, which are just like sequences of words. So what we're going to do is we're going to build a probability model of the transition distribution. Given your history, what's your next job? And so just from one resume, if they have, say, 21 years of history in their resume, that's 21 next job prediction in my prediction that would enter my prediction corpus. Okay? So, and the thesis here again is that getting a quality representation from this incredibly high dimensional space of possible sequences of jobs and mapping that down to a low dimensional vector is the really hard part. And even if I'm not training for the thing I ultimately care about, wages, I can learn a lot about that from really big data sets. And so that's what we do here. So in terms of, then the next step is fine tuning. So we can take that, foundation model that was designed to predict the next job, and we can fine tune it on a different data set with a different outcome and a different objective. So instead of just trying to predict the next job in a longitudinal government survey, we can try to predict the wage. So I put up here, this is like not really helpful for most people, but just to show our paper, if anybody's actually like curious about equations, some people like equations, like we do actually in our TLMR paper, like write down the equations for the neural net in a way that would be familiar to someone who came from more of a traditional statistics or econometrics background. And so we can think of this as like, it's a nested logistic model where there's a probability of staying in the same job, and then a multinomial logistic, which says conditional on switching jobs, which job do you switch to? And it's just like traditional logistic regressions, except for one thing, we have latent representations of our covariates and our history rather than sticking them in directly. And then how do we come up with those latent representations? We're using this attention framework from the transformer models, which basically says we're going to learn for every job both what's important, what's important about that job for predicting the next job, but also for this particular job, how important is it to look at 10 periods ago or 5 periods ago? And so that attention component is going to give us higher quality representations. And that was one of the breakthroughs that led to the success of the language model. So we just copied it here. So this is basically just the same model that's used for ChatGPT, except for we add this special probability of staying, and we also bring in covariates. And that's because, you don't have repeated words in language, but you do have a lot of repeated jobs. So the fine tuning part is the part where I think we're going to have a big research literature. How do you fine tune and how you fine tune, in my view, should depend on your downstream task. And that's the successful innovation we had in, like, say, heterogeneous treatment effect literature, and we can use the same insights here. In terms of the fine tuning context, the pre-training step, which here we're doing ourselves, but in subsequent papers, we use OpenAI's pre-training, or we use Llama's pre-training. But in this paper, we're using our own pre-training on resumes. We come up with a function that maps from histories to a low dimensional representation parameterized by theta, and theta are the parameters of the neural network. Then we update those parameters by continuing stochastic gradient descent estimation of the parameters of that representation function, the parameters of the neural net. So just because the last gradient steps took a gradient for next job prediction, the next gradient step, when we continue the training, will instead put in mean squared error prediction of wages, for example. But in my next papers, I'll show I want to change that. I don't just want to do that, but this is the easiest thing to do and to understand. I took a gradient and I was moving my theta hats in a certain direction according to next job prediction. Now I start putting in observations from a new data set and I move that theta hat to try to predict wages. And so it's just like so simple. Like you just program another gradient and keep going. You know, it's kind of an amazing thing about stochastic gradient descent. It's so nimble. Like I don't have to get into the guts of how you got here. All I have to do is write down my objective and keep going. So from an engineering perspective, it's like the simplest thing I've ever done. Especially because they're really good tools to do the stochastic gradient descent. So we don't even write a lot of our own code for that either. So then we can think about comparing different classes of prediction models. The classic in econometrics was just a linear regression based on handcrafted summary statistics. And a literature with thousands and thousands of papers had sort of converged on a set of summary statistics. So this isn't just like something I made up. These are the things that people found after running lots of hand regressions, but that these were the things that should matter. We also, to give it regressions a running shot, we also throw in some lasso models with more covariates. And then we also compare it to our model, which takes a shallow neural network on top to predict wages on top of these representations. And so we look at out of sample R squared for these regressions. And again, the coarse grained regression is the result of thousands of people running lots of regressions to kind of maximize R squared. What we find is that our approach gets to much higher R squared. And we break things out to try to see what's important. Is it just important to have a really rich model with lots of parameters? Is it important to have pre-training? Surprisingly to me, I would have thought doing this just on a data set with like thousands of people would do terribly. We have 950 dimensional latent vector that would do terribly, way over parameterized. But even without the pre-training, it does pretty well. That's the 0.491 R squared. But when we add in the pre-training on the resume, we get a big kick in terms of predictive performance. Okay, so that's basically prediction. And so the first point I wanted you to take away is that using pre-training on, even with the wrong objective, if you have a much bigger data set, but that just has something to do with the thing you care about, then you might be able to actually, if you just think about a tech firm, like if you have this huge bunch of log data of like everything people did, you may be able to just build a model of that log data and come up with a representation of things you observe about people and map it into a lower dimensional vector that's predictive of what happens next. And that might not really have anything to do with your downstream task, but it might be very predictive. And that might in turn help you get more power in randomized experiments if you stratify according to these things, or it could help you reduce the variance in an experiment if you control for these things, control for their pretreatment differences. So it can have all sorts of use cases that would be very powerful. Now let's try to do something. Again, this is not going to be causal, it's going to be decomposition, but the methods would apply similarly if it was causal, the gender wage gap. So in terms of thinking about, let me skip to here, decompositions versus causal effects. So if we thought about gender as being a treatment, and we assumed there was unconfoundedness, forgetting about what that means for a second, or whether that could ever mean anything. But if we just thought of gender as a treatment, one thing you could use under unconfoundedness is that the difference between potential outcomes between men and women can kind of boil down to the expectation over possible histories of the wages conditional on history. And so this part of it is kind of targeted for decompositions, where what we're trying to do is figure out what's the gender wage gap. So the fact that in causal models, we think about like maybe trying to hold fixed across two groups the marginal distribution of histories, and then and then make comparisons for two people who have the same history. That's a key part of causal analysis. For decompositions, we have something similar we're caring about, which is the explained gender wage gap. We want to know like how much of the difference between men and women can be explained by history. And then anything left over is, you know, it's something we need to reason about. It might be bargaining, it might be discrimination, it could be something else. So, but people don't the interpretation part is usually like a downstream exercise. The first question is just, I want to understand how much of differences can be explained by history. And if you want to think about why that's important for policy, just imagine for a second that I told you, say, you know, women make 80% of men. But then I told you, actually, conditional on history, they make the same thing. Then from a policy perspective, you'd say, oh gosh, I should think about studying like what majors do people have, and what makes them stay in the labor force, and what makes them choose different careers. Like, I don't know for sure that that's where I should look, but that's really suggestive that like the choices people are making to get to a certain career path is important. On the other hand, if I found that conditional on history, women were making something really different than men, then first of all, I might want to say, well, have I really measured history correctly? And what am I missing? And I'm going to show you in a minute, you are missing stuff in the way people normally measure this. But you might also think about like bargaining and, you know, coaching people about how to get their wages up and stuff like that, which, you know, if you saw a big discrepancy, people with the same history, same jobs getting different wages, there's a bunch of other policies that might be interesting. Of course, none of that it wouldn't be definitive, but doing these decompositions can kind of point you in different directions for further causal analysis. Okay, so now to get into our contribution, if we think about the gender wage gap in this context, we would be trying to analyze the expectation over history. And the key is that on this outer expectation, we would be applying the same distribution of histories for men and women. So it's not, that's why it matters. There's like a single expectation with a fixed distribution of histories. And you can do this different ways. You could take it the male histories, the female histories, the joint histories, but the key is that you've got this, you're on the outer expectation, both men and women are being evaluated with the same histories. And on the inner expectation, we've got the difference in wages between men and women with the same history. So this is the estimand for this literature. So I didn't make this up. This is what this is what the literature is targeting. If you wanted to use representations, and we would say, well, we just can't do that. The top line, A1 minus A2, that's not feasible. Too many histories, not enough data, not enough people, impossible to estimate. But if I use representations, maybe I can get that down to, you know, a 1,000-dimensional vector. Maybe if I have enough people, I could actually estimate this thing. So if I had a good representation, lambda of h, maybe B1 minus B2 as an estimand might be something I could target. But that relies on me getting a good lambda. And so typically, if I just did predictive fine tuning, I would be trying to make A1 and B1 the same. I would be trying to predict wages well for women, and I would make A2 and B2 the same. I would try to predict wages well for men. That's the prediction objective. But the causal objective is the difference between the two. I don't care if I actually get the whole thing off by a level. What I do care about is if I miss something for men and not women, or I miss something if I do something that affects this difference. And those are admitted variables, or those would be confounders in the causal inference language. So if when the process of going from H to lambda of H, I leave things out, I will create omitted variable bias. So there's a lot of different ways to write this down. We've got a way to write this down that makes that we then operationalize in our theorems and our approaches. So we could write down the omitted variable bias as a function of lambda. This is the omitted variable bias due to lambda of h omitting things. Okay, and so here what matters is the covariance between leaving something out that matters for wages and leaving something out that matters for gender differences. So if there's a part of history that predicts whether you're a man or a woman, and it predicts wages, and it's not in lambda of h, this omitted variable bias will be big. Okay, so writing it this way tells us what we really need to target to have these work well. Now, the first observation that everybody makes is, well, okay, this is not an infeasible objective because I don't know these functions ey given h and I don't know the log odds with the true h. That's my whole problem. I don't know what they are. But the heterogeneous treatment effects literature has developed a number of objectives which have been shown to be good objectives for minimizing something like this. So for example, in the heterogeneous treatment effect literature, we look at the R-learner objective. That's by Nie and Wager, and that's the objective we use in generalized random forest. That it's based on the Robinson regression for semi-parametric econometrics. And so what that objective basically says is, I'm going to take the residuals from a regression of y on x, and I'm going to regress them on the residuals from a regression of the treatment on x. And I'm going to have coefficients on that in that regression that depend on x. And if I can minimize this difference, the squared difference, this R-learner objective, then I will have done a good job with estimating heterogeneous treatment effects. Our observation is that also means you would do a good job with omitted variable bias. It's exactly things that are things that are residuals from y on x and residuals from w on x. The things that are related to both of those are the things that we need to control for. So we introduce a fine-tuning objective, an approach that targets that objective. Here now it's a little complicated because we've actually got 3 places that the representation comes in. It comes in the wage prediction model, in the gender prediction model, and in the treatment effect model, and we iterate between those in our fine-tuning. We do some semi-synthetic simulations where we draw a data set and estimate the unexplained wage gap and compare it to the truth, which we know from in our simulations. And we look at a couple of different approaches to fine-tuning, that all of which are trying to target this omitted variable bias, all of which are trying to target both the gender prediction and the wage prediction. Multitask fine-tuning just goes back and forth between predicting both. We have a projection-based fine-tuning approach we don't have time to go into, and the difference-based fine-tuning is the R-learner objective. And we show that the R-learner objective gives us the biggest improvements over no adjustment. So based on that, we operationalize that. The second thing we do is we prove a theorem, and this theorem is very close to the theorems from the standard double machine learning, AIPW, applied causal inference literature. And there's one big difference. The standard result, which I showed you at the beginning of the talk, would talk about having a good model of, in this case, gender prediction, and a good model of wage prediction as a function of the true underlying covariates, in this case would be H, but the histories. But we're only requiring our models perform well as a function of representations of history. So instead of, having a billions and billions dimensional space where we're claiming that we have models that converge at the root and rate with, in principle, billions of indicator variables for histories, which would be implausible. Instead, we're saying, oh, we've got models that converge as a function of a low dimensional representation. But that only works if we have low omitted variable bias. And this decomposition into saying, if we have representations that don't omit stuff, or the omitted variable bias goes to 0 at a good rate, then we only need to worry about a much simpler predictive model. And then we get good estimates. So let me now show how we apply that. And one of the reasons this is fun for me is that I think it's hard to look at a language model or a transformer model and say, like, well, why does it work, or how does it work? But now that I have like a very specific causal task, I can come up with interesting ideas of how to tell you, why my model is better or why it works well. And so what we did here is we just built a prediction tree for wages as a function of our representations, our low-dimensional representations. And then a tree will put observations into groups. After we've put them into groups as a function of the representations, which are uninterpretable, we then look at what are the most common jobs for people in that group, okay? And so with those historical jobs. And so that allows us to see what was left out. And so at the top, we have jobs at the level that they go into wage regressions, these like 330 jobs. And so if you were doing a wage regression, you would say, are you a manager? And you have an indicator variable for manager, and that would be used to predict wages. These lower level boxes are groups of representations, and that's kind of what our model is going to add to the regression over and above these indicator variables for your last occupation. Okay, and so what do we have in there? Well, if you look at manager, this is going to show you what's the omitted variable bias we're finding. If we look at manager, people who have a history of software developer and electrical engineer have higher wages, and it's an 11% female group. So if you leave out a history of software developer from a regression of wage on manager, you are leaving out very important things about your history. And similarly, if you had a background as cashier and homemaker and you're a manager, you're 93% female and you have lower wages. So those are the omitted variables that go away if you try to use regression-based approaches, but that get picked up by our low-dimensional representations of history. And truck driver, machine operator, a similar type of thing. And of course, once you look at this, you can say, well, you should have stuck that in the regression. What an idiot are you? You didn't put software engineer in the regression. But the problem is, like, there's too many things in history. Like, you can't, Lasso doesn't pick them up either. Like, you can't pick up all of these variables, and because there's just not enough data. But the foundation model allows you to reduce the dimensionality enough to capture what's really important in a data-driven way. So if we then finally go to the real data, we look at the unadjusted gap. This is just the difference in means between men and women, which expressed as a ratio of the ratio of women to men. It goes from around 0.75 up until the low 80s. If you use Lasso to adjust for handcrafted covariates, that closes a lot of the gap. And our model closes about a quarter of the remaining gender wage gap, which basically says that another way of saying that is if you stick in these types of things into gender wage regressions, you explain some of the otherwise unexplained gaps between men and women. It's not because the women didn't bargain hard enough conditional on being manager. It's that you can't get the same wage being a housekeeping manager as you can being a software manager. So asking people to bargain harder isn't going to help with that problem. What might help is getting people on different, educational or career paths earlier on in their careers. Then I'm just about out of time, so I thought I might be. So I just want to advertise this other research agenda where we're actually currently in the middle of revising this, and within a week or two, we'll have a new version up. But we've been trying to then substitute this basic foundation model that I showed you with a LLM-based foundation model. And the idea is, again, sequences of jobs are like sequences of text. That's how we were able to use transformer models in the last paper. But now what we're going to do is we're actually going to take an observation from a tabular data set and write a little subroutine that turns that tabular observation into text. And so this is an example of what taking an observation from the NLSY or PSID government surveys and turning them into text looks like. And then we can prompt an LLM with this text as history and see what it says about what job should come next. Now, there's a couple different ways we could do that. One is we could take the embeddings and stick them in a multinomial logistic regression, and maybe use a shallow neural net to regularize it or something. That would be sort of similar to what we did with the wages before. A second thing we could do is we could just query the OpenAI API and see what it pops out. A third thing we can do is we could do some fine tuning using, say, Llama, or you could also fine tune with OpenAI, but it's just very, very expensive. So we do it with Llama and try to predict the next word. So this equation kind of tells you what we are doing. You can think about the next job prediction is it's a probability, conditional probability of having a particular job as a function of your history of covariates and your history of jobs. And we're going to estimate that probability by applying a large language model where the prompt, the thing to the right of the conditioning, is this text template. And then what it's going to spit out is a probability of a next word. And we can calculate the probability of the next word and turn that into a probability of a job. And so what we find, the TLDR, is that the first two approaches actually don't work. The number two doesn't work because it hallucinates jobs that aren't jobs, but also because it just doesn't know all the conditional probabilities. Like reading Reddit doesn't tell you exactly the probability of being a machine operator in the Pacific Northwest. It actually helps to have data. Just reading the text of the world doesn't help. But if you understand the basis of knowledge from text in the world and then fine tune it on actual data, you get better predictions. So number three is the winner, and it beats our custom model, which was sad for me because we built the custom model and we liked it. But it's good for the world because actually it was expensive and time consuming for us to build a custom model. And what this suggests is that this kind of approach of taking tabular data and turning it into text, in some cases, if the text has meaning, that can be a very simple approach. In some of our analysis, we try substituting these words like cashier for numbers, for codes. That does not work as well. So this particular approach may work well. Like cashier actually has some meaning in language. And that is one reason that for this type of prediction problem, the large language models work well. So I will stop there and happy to go to questions and discussion.